Why is it more difficult to stop a car than a bicycle moving at the same speed? Well, the answer for that has something to do with our topic for today, which is all about momentum. An amazing science. At the end of this lesson, you should be able to use the law of conservation of momentum to solve one-dimensional collision problems and explain the contributions of scientists in our understanding of mass, momentum, and energy conservation. Which is more difficult to stop? A truck or a motorcycle moving at the same speed? Yes, you're right, it's the truck. Now what about two identical motorcycles moving at different speeds? Correct, the one with a higher speed. Now given these situations, what factors or quantities affect the resistance of these objects to stop? Definitely, it's the mass and velocity. The product of this mass and velocity is especially termed as momentum or linear momentum, symbolized by smaller p, which stands for progress, and was first used by the German scientist Gottfried Wilhelm von Leibniz, who defined progress as the quantity of motion with which a body proceeds in a certain direction. Momentum is a vector quantity, since velocity is vector. So, it's pointing in the same direction as the velocity, of course. Momentum is also considered as inertia in motion, with the formula P is equal to m times p, where p is momentum, m is mass, and v is velocity. The SI unit for momentum is kilogram meter per second. So, the amount of momentum which an object has is dependent upon two variables. One, how much matter is moving, and two, how fast the matter is moving. So going back to the opening question, why is it more difficult to stop a car than a bicycle moving at the same speed? Obviously, the car which is more massive has more momentum than the bicycle. Therefore, it is more difficult to stop. Could it be possible for a small object and a slow-moving object to have large momenta? Yes, of course. For a small object to have large momentum, it should move at a high velocity, just like the bullet. While for a slow-moving object to have large momentum, it should have a large mass, just like this bus. Let's consider this. Which has greater momentum? A 10,000 kilogram elephant at rest or a 1,000 kilogram car moving at 10 meters per second? Take note that the elephant is at rest, so its velocity is 0, while the car is moving at 10 meters per second, though its mass is 10 times smaller than the elephant's. So if we're going to calculate the momentum of the two objects, the elephant's momentum is 0, while the car's is 10,000 kilograms meter per second. Therefore, the car has a greater momentum. Is it possible to change the object's momentum? Yes, of course. How can we change the object's momentum? To change the object's momentum, we can change either the mass or velocity. In most cases, it is the velocity. So, our formula is delta P equals m delta V, where delta V is the change in velocity. When the velocity is changed, it means that the object is accelerated. So, when we say acceleration, it's the rate of change in velocity per unit time. In equation, A equals delta V over t. Simplifying further, A equals Vf minus Vi over t. Now let's use Newton's second law of motion. F is equal to m times A. F is force, m is mass, A is for acceleration. Knowing acceleration is equal to delta V over t, so the formula will become F is equal to m times delta V over t. Rearranging the equation will give us Ft equals m times delta V. And since delta V is Vf minus Vi, therefore Ft equals m times Vf minus Vi. So to distribute this, we'll be having Ft equals mVf minus mVi. mVf is the final momentum and mVi is the initial momentum. Therefore, Ft equals Pf minus Pi. The final formula will be Ft equals delta P, or the product of force and time is equal to the change in momentum. So what causes the change in momentum? From the derived equation, an external force acting on an object over a specific time leads to a change in momentum of the object. So the product of this force and the time of the force that acts is especially termed as impulse, with the formula I is equal to F times T, where I is impulse, F is force, and T is time. The unit for impulse is Newton's second, which means that it measures a change in momentum because it is not always possible to calculate force and time individually since collisions happen so fast. Impulse is also a vector quantity in the direction of the force. As shown in the equation, force and time are inversely proportional to each other. So, a change in momentum in a short time requires a large force, just like this. And a change in momentum in a long time requires a small force, like this. Let's now use the concepts to these sample problems. A 50 Newton force is applied to a 100 kilogram boulder for 3 seconds. Find the impulse. To solve for the impulse, we'll have the formula I is equal to F times T, given the force 50 newtons and time 3 seconds, so we'll substitute them and get the impulse for 150 newton second. Note that we didn't need to know the mass of the object in the above example. Next, if the halfback experienced a force of 800 newtons for 0.9 seconds to the north, determine the impulse and the change in momentum. So to solve for impulse again, we use I is equal to F times T. Since force is 800 newtons and time is 0.9 seconds, therefore we got impulse 720 newton second. Since I is equal to F times T and Ft is equal to delta P, then delta P equals m delta V equals 720 kilogram meter per second. The impulse is 720 newton second, while the change in momentum is 720 kilogram meter per second. The two quantities are numerically equal, but they differ in their units. Why do we bend our knees as we land to the ground after jumping? This is to lengthen the time of impact, which causes the force of impact lesser and avoid injuries. Next question. How do karate experts break a board or block by hand? They need to make it very quick to lessen the time, which results to an increase the force of impact that is enough to break the board of block.